This is a lecture from OpenTuition. To benefit from the lecture, you should download the free lecture notes from opentuition.com.
All right, we're now going to look at something called the normal distribution, which, as you'll see, makes big use of the standard deviation that we were calculating in the previous chapter. And although there's really just a couple of rules you need to learn as far as normal distribution questions are concerned, it is rather important that I sort of explain what's going on. So be patient with me for the first bit of this lecture, where I want to explain what's happening, and then I'll show you the rules that we actually use. And I need, first of all, to remind you what a histogram was. And so look at example 1 in this chapter. It says the following table shows the annual salaries earned by 150 workers. So it was 0 to 1,000, there were 25, 1,000 to 2,000, there were 35, 2,000 to 3,000, there were 40, and then we had a group 3,000 to 5,000, there were 50. So in total, let me check I've written it down right, 150. All right, well, if you remember the histogram, and forgive me, I've not got a ruler here, so I'm not going to be terribly pretty. Along the bottom, we have the ranges. So it was 0 to 1,000, 2,000, 3,000, 4,000, 5,000. And we drew bars upwards, so to speak, depending on the frequency. So 0 to 1,000 there were 25. So let's suppose that's 25 units. 1,000 to 2,000 there were 35. Let's say is there. 2,000 to 3,000 there were 40. 3,000 to 5,000 there were 50. Now I did make the point in the earlier lecture, and you'll see why it becomes so important in a second, that it's not the height of the bars that's proportional to the frequency, it's the area. And the problem here, you see, is here the ranges were 1,000, not to 1,000, 1,000 to 2,000, 2,000 to 3,000. But all of a sudden, we've got a range 3,000 to 5,000. And if I did a bar 50 units high, oh dear, it would just be terribly misleading. It looks as though everybody's up there, whereas in fact, because the width is twice as much, the range is twice as big, we need to do a bar that's half the height. So instead of having it 50 units high, we'll have it 25 units. And that surely is a bit more meaningful, because you see between 3,000 and 5,000 there are 50. I don't know this spread evenly, but you know, if they were, there'd be 25 between 3,000 and 4,000 and 25 between 4,000 and 5,000. The histogram there is much more representative, but always it's the area, the width times the height, that is proportional to the frequency. Having said that, look at B. It says calculate the probability of a worker earning between 1,000 and 2,000. Well, of course, in the original table, that's easy. We dealt with that way back in one of the earlier chapters, that between 1,000 and 2,000 is 35 out of a total of 150. 35 divided by 150, the probability is 0.23333. However, and this may seem silly, but it's because of what's coming, just imagine I hadn't given you that table, but all I'd given you was a correctly drawn histogram. That's all I'd given you. And I said to you again, what proportion earn between 1,000 and 2,000? Well, you know that the area of that bar is proportional to the number of people in that range. You know that the area of all the bars is everybody. The total area of all the bars is proportional to the total number of people that were asked or in the sample. And so, and don't worry, you'll never be doing this in the exam. I'll tell you, I'm introducing what we're going to do with normal distribution. But if I gave you that histogram and you had a ruler, if you could measure that area, how many square millimeters or whatever is it, and take it as a proportion of the total area of all the bars, then again you'd come to 0.23. Because the area of that bar is proportional to 35, the total area of all the bars is proportional to 150. And again, C, calculate the probability of a worker earning more than 2,000. Well, again, with the table, easy. More than 2,000 is there. 40, 2 to 3, 50, 3 to 5. So a total of 90 out of 150. It's 0.6 or 60%. But again, imagine that I hadn't given you the table. All I'd given you was a properly drawn histogram. Well, more than 2,000 is that bar and that bar. The total area of those two bars is proportional to the number of people between 2 and 5,000. And if you took that as a proportion of the total area of all the bars, that's proportional to the total number of workers. And so divide the red area by the blue area, and again you end up with 0.6. Now, why have I mentioned that? What I've just said applies to any properly drawn histogram, that the area in the bar is proportional to the number in that range. The total area under all the bars is proportional to the total number of people. But we could, if you like, smooth it out. You know, if I had smaller and smaller ranges, if it was groups of 500 instead of 1,000, or groups of 10, gradually this would turn into a curve. And we call it a frequency curve, a frequency distribution. And again, if I told you, oh, we've looked at the annual salaries and it forms this sort of pattern. 0, 1,000, 2,000, 3,000, 4,000, 5,000. So if I gave you that curve, all it is a smoothed out histogram. And if I said to you, oh, what proportion earn between 0 and 1,000? Well, this area here, it's only a smoothed out histogram. That area there is proportional to the number of people between 0 and 1,000. The total area of all the bars, or the total area under the curve, is proportional to the total number of people in the sample. And so if I worked out the red area as a proportion of the total area, that would be the proportion of people in that range. Well, finally, I can get on to the normal distribution. Because for one particular shape of curve, there are tables which let us work out those proportions. And the particular shape is called a normal distribution. And it looks like this. Now, strictly, it's got a very, very precise equation. It's a very precise curve. But any curve that's more or less this shape is a good enough approximation. And the main things are that it's symmetrical. So it's the same on both sides. You know, you've not got that, for instance, which is bent. It's symmetrical. It's like a mirror image of itself. Strictly, it never actually touches the axes. It gets very, very close, but there's always a chance of being anywhere. And there's only one mode. What I mean is this. A curve this shape, whoops, can be symmetrical, same both sides, but you've two peaks, you've two modes. Well, a normal distribution, it looks like a bell, as you can see. Now, as I said a minute ago, for a shape, for a curve that's that sort of shape, there are tables help us get these proportions I was talking about without needing a ruler and having to actually measure the areas. And to show you how we use it, look at example 2. A company produces units with an average length of 10 centimetres. So obviously, if that's the average, some units are bigger, some units are smaller. If it's a normal distribution, which is what we assume, then the average is in the middle. It's 10 centimetres. It's got a standard deviation of 0.2 centimetres. I'll come back to that. That's a measure of spread, remember. But it says what proportion of the units will have a length, first of all, that are more than 10 centimetres. Well, that's easy. To be more than 10 centimetres, well, 10 centimetres is the average. Remember, our curve is symmetrical, so there's as many as above as there are below. And so surely 50% or 0.5 will be above the average. But what about B? It says what proportion are between 10 and 10.4 centimetres? Well, 10 centimetres is the average. 10.4 centimetres, let's assume, is there. Well, think back to what I said about the histogram. What we could do is get a ruler and start measuring, because the proportion under the curve between 10 and 10.4, so this area there, would be proportional to the number of people in that range, or the number of units in that range. The total area of all the bars, or the total area under the curve, would be proportional to the total number of units we were looking at. And so what you could do is get a ruler, or if you got that on a piece of graph paper, you could start counting little squares. But if that red area is, let's say, a third of the total area, it would mean a third of the units are within that range. If the red area was a quarter of the total area, it would mean a quarter of the units were within that range. Well, with a normal distribution, we don't have to go around counting squares on graph paper. We can look up on tables, and you're given the tables. You can look up the area under the curve, any area between the mean and some other point, as a proportion of the total area. The only thing is, though, the proportion very much depends on the spread. you know, if all these units were very, very close to 10 centimetres, then to be 10 to 10.4 would be nearly 50%. But on the other hand, if these units are very widely spread, the proportion between the average 10 and 10.4 is going to be much smaller. And so when we use the tables, we look up the distance away from the mean in numbers of standard deviations. We call this measure Z. And what Z is, again, it's the difference from the average, the mean, in numbers of standard deviations. Z equals x minus x bar over the standard deviation. How far away is it? Well, 10.4 as against 10. We're 0.4 centimetres away. What is the standard deviation? It says here the standard deviation is 0.2 centimetres. And so 10.4 minus 10 is 0.4. Divide by 0.2, it's 2 standard deviations. And we can use that. We can look up in tables what the proportion is that lie within that range. Now you get given the tables in the exam, and at the beginning, on one of the first 2 pages of the lecture notes, and I want to look up the proportion that are 2 standard deviations away. Well, if you go down the side, down the column, it's at the end on the left-hand side, it's 0.0, 0.1, 0.2, 0.3, 0.4, and so on. And as you go along the columns, well, the first row is 0.00, 0.01, 0.02. The second row is 0.10, 0.11, 0.12, and so on. Well, what do I want? I want 2.0. So it's 2.0 down the left-hand side. And then as you go along the columns, you get 2.00, 2.01, 2.02, and so on. Well, from the tables, 2.00, it's the 2.0 row, the 0.00 column, you get 0.4772. And what does that mean? It means that the proportion 0.4772 of units are between 10 and 10.4 centimetres. 0.47 or 47.72% of them. Check you've got it. Let's look at the third one. C. Whoops. It's the same problem. So there's our curve. The average, remember, is in the middle and was 10 centimetres. But what does it want? It wants to know what proportion will have a length of less than 9.8. Well, if 9.8 is there, to be less than 9.8 is here. And so what we want is that red area as a proportion of the total area. But again, think back to what I said earlier. These tables, we can only look up areas between the mean and some other point. So how are we going to do it? Well, I know what proportion are less than 10. It's symmetrical. And because the mean is 10 centimetres, to be less than 10 is 0.5. this area here. How can I get 9.8? We can look up the proportion between 9.8 and 10. We can use the tables for any area between the mean and some other point. We look at the distance away, it's z-score. Well, z, the difference between the mean and the point, which is 0.2, divided by, sorry, I'll write it down, x minus x bar over sigma. So the difference between, doesn't matter whether it's plus or minus because it's symmetrical, but 10 and 9.8, the distance is 0.2. The standard deviation is 0.2. So the z-score is 1.00. And so look at the tables again. To be 1.00 from the average, 1.0 down the left-hand column, 0.0 across the top, 0.00, I get 0.3413. We're not there yet, because remember, I know that less than 10 is 0.5, 50%. I now know that between 9.8 and 10 is 0.34 or 34%. Well, if this is 34% and if the total is 50, surely what I want, less than 9.8, is the difference. So less than 9.8, 0.5 was less than 10, minus 0.3413, between 9.8 and 10, the answer is 0.1587. That's the proportion of our units that'll be less than 9.8, 0.1587 or 15.87%. So it's not hard. Just one thing though that could happen is having to use the tables backwards. Look at example 3. For the same question, it's asking us to work backwards. Remember our normal distribution. There we are. The average is 10 centimetres. Here it says there's a 0.95 probability that the length will be more than x centimetres. And he wants to know what x is. You know, is x 5 centimetres, 8 centimetres, 15 centimetres? Well, they want to be a 0.95 probability that it's more than x. Well, remember, because it's symmetrical, there's a 0.5 probability that it's more than 10. And therefore, for there to be a 0.95 probability, x must be somewhere down here. And we want to know what x is. And so the area more than x, that area there must be 0.95. How are we going to do it? Well, we already know more than 10 is 0.5 because it's symmetrical. And so the area between 10 and x must be the remainder, 0.45. Now, how can I get that? You know, before we knew the z-score, and we could look up on the tables and it would give us the probability. But here we'll have to use the tables backwards. What z-score will give us an answer of 0.45? Let's have a look. If you go down the left-hand column, 1.00 gives a z-score of 0.3, gives a probability of 0.34, sorry, 0.3413. Well, I want 0.45. What about 1.90? Well, that gives 0.4713. That's too much. Look at 1.60. 1.60 gives us 0.4452. If we move along, 1.61 is 4463, 1.62, 4474, 4484, 4495, 4505. Z must be 1.64 or 65, perhaps a bit halfway between the two, because 1.64 would give us an answer of 0.4495. 1.65 would give us an answer of 0.4505. Now, in fact, it doesn't matter, but it is slightly nearer to 1.64 if we had more detailed tables. So Z is 1.64, but remember what Z is. Z is the distance from the mean divided by the standard deviation. Well, we know the z-score, 1.64. We know the standard deviation, what was it, 0.2. And therefore the distance from the mean, oh dear, my writing, must be 1.64 times 0.2, which is 0.328. And so now I can get the answer. We wanted to know what x was. X, remember, is where 95%, 0.95 are bigger than that. And because of symmetry, 0.45 are between x and 10. We got the z-score and worked backwards. The distance between x and 10 must be 0.328 centimetres. Therefore, x, 10 centimetres minus 0.328 is 0.672 centimetres, 9.672. We can say that 95% or 0.95 probability of a unit being bigger than 9.672 centimetres. Now that I appreciate is a bit messy, so look back at example 2 and then again at example 3 and make sure you've got it. And how we use the tables when we know the z-score.